Hello everyone, my name is Bhushandeep Sharma and welcome to our presentation on the Espresso algorithm, a method used to minimize Boolean function in digital circuit design. Today we are diving into how this algorithm helps us simplify complex logic expression and why is that essential for building efficient low power circuit. Imagine designing a digital circuit with hundreds of variables, the complexity can be overwhelming. Traditional methods simply can't keep up. This is where the espresso algorithm comes into play, offering a practical heuristic approach that brings order to chaos. Now we will discuss about the need for the logical minimization in Boolean logic. Before we explain the detail of espresso, let's talk about why minimization Boolean function is so critical. In digital design, every logic gate consumes space, power, and generate heat. When a Boolean function is implemented directly from its full truth table, the result is often an overly complex circuit that inefficient and costly. By minimizing these Boolean expressions, we reduce the number of logic gates required. This reduction not only minimizes the physical size of circuit but also decreases power consumption and increases overall speed. In short, Boolean minimization is about optimizing hardware so that modern system can perform reliably while remaining cost effective. Now we will get into the historical background of logical minimization. Engineers relied on methods like Carnot maps and Quinn-McCluskey algorithm to simplify Boolean functions. Carnot maps, developed in 1950, provide a visual means to simplify expression with up to about six variables. However, as digital circuit grew in complexity, these maps become impractical. The Quinn-McCluskey algorithm offered a more systematic approach and could handle a. Now let us see some limitation of the traditional method and why we need espresso algorithm in logic minimization. Boolean minimization with 50 plus inputs in NP complete is a NP complete problem comparable to traveling salesman problem. Let us take an example of traveling salesman problem. A traveling salesman want to cover 50 city. He can have a 50 factorial path, that ways that he can cover the cities. So that become very exhausted enumeration, so that become very infeasible, and Carnot maps is only limited up to 4 to 6 variable, and Quinn-Mikulski algorithm become impractical beyond 10 to 15 variables. But in modern digital system we have hundred of variable, so we here need heuristic approach that find near optimal solution for it. Espresso algorithm is based on stimulated annealing method. uh, it firstly start from initial cover, like very basic implicant, like from, and then it covers the prime implicant by traversing in different direction, like you have three variable. First you will look for a variable in y and traverse in different direction, like in z direction or y direction, and find for a local minimum point. And you have to do this in iterative manner and look for the global minimum point where you can minimize your boolean function. As we know, our espresso algorithm is a heuristic in nature. Now we will discuss what is heuristic algorithms. Heuristic algorithm finds good enough solution. That means that never guarantees that they provide optimal solutions. They only take your result to good enough solutions. These method trade mathematical optimality for computational efficiency. A heuristic means to find. This is based on experience and effective patterns. The key characteristics of heuristic algorithm are to find, not guarantee optimal solution, significantly more efficient than exhaustive method, as it does not find all the prime implicants, and it produce consistent and reliable result in practice. Now we have covered the basics for our espresso algorithm. Now let's introduce espresso. Unlike exhaustive search method that try every possible solution, espresso is a heuristic algorithm. This means uses rule and iterative approximation to find a solution that is good enough, a near optimal result rather than the absolute minimum. At its core, the algorithm works on Boolean functions represented in sum of product form. It breaks down the function into three sets: the onset, the offset, and the don't care set. Where the onset is the function whose output is 1, and the offset where the output is 0, and the don't care set where the output can be either 0 1, giving us flexibility during minimization. One of the elegant feature of Espresso is it uses cube notation, a way to geometrically represent Boolean function. Each cube is an n-dimensional space represent a group of input condition where the function behave similarly. This visualization not only simplifies understanding but also aids in the minimization process itself.
Now I am going to explain the algorithm of ESPRESSO. In mainly we have three fundamental steps in ESPRESSO. The first one is expand, then the second one is irradiant cover, and the third one is reduce. Now we are going to explain one by one. What is expand, what is irradiant cover, what is reduce in Espresso. Expand is grow each cube until becomes prime number. Just take an example in X direction, Y direction, and Z direction. Expand the cube until the it becomes a prime. That is called expand in short manner. And coming to the irradiant cover, reduce number of prime cubes. That is identify and remove redundant cubes which we have na redundant cube, just reduce them in irredundant cover function. And coming to reduce function, replace cubes with smaller contained cubes. We have some smaller cubes in the larger cubes, those we have to reduce them and start executing and create starting point of next iteration. When coming to the expand operation in detail, starting with initial cover of the function, for each cube in the cover, try to complement each literal in turn, and next test if resulting cube is contained in onset. Okay, if yes, remove the literal. That is the expand the cube. Continue until each cube is prime. That's the main motto of these function, expand function. Mathematical formulation given, and the result what we are expecting from the expand operation is each cube becomes maximally expanded to a prime implicant. That's our result in the expand operation. And then next, expand operation visualization, starting initial cube, and we have an expand cube, and then we have prime cube which cannot be expand further. Mm, then coming next to the second function, irredundant cover operation. In that we have classifies the prime cubes into two categories. One is relatively essential cubes, and the other one is redundant cubes. In relatively essential cubes, we cannot be omitted. That's like we are particularly mentioned that those directions and those functions we cannot minimize them. And coming to redundant cubes, can be removed while maintaining coverage. These cubes can be removed to minimize the function. And redundant cubes further divided into two more. One is totally redundant and partially redundant. Totally redundant, we can simplify those function, and partially we have to carefully observe and reduce those functions. Use minimal coverage procedure to select the smallest subset, similar to selecting minimum number of prime implicants. Irradiant cover visualization. One, we have some part of cubes and the classification and the minimum cover. Uh, and coming to the third part, reduce operation. Reduce operation, we have transforms prime cover into new cover with smaller cubes, creates starting point for the next iteration that may lead to the better solution. Helps escape local optima in the solution space. For each cube in the cover, find the smallest cube contained with it that still covers essential vertices, and replace the original cube with this smaller cube. Coming to the ESPRESSO algorithm, we have I am going to explain the algorithm how it works. First, we have function original function which we have contain onset. In that onset, we have prime implicants, which says with the expression. Yeah, onset which is we have prime implicant, like for example 1 1, which we have gone through the K map, which we have 1 1. That's the given expression. We have put it in original function. And coming to the offset, we are putting in the r offset with the zero values. And coming to the dc set, in the dc set we have don't care don't care expressions. These are the three sets. And now we are going to expand, we are going to use the expand function, which we have two arguments. One is f original function with original, and the r which is offset, which and coming to the irredundant function, we have uh, two more uh, two more arguments. One is the previous f function stored argument, and the other one is the don't get set. uh, Coming to the loop, do while function reduce function and expand function and irredundant function. You do until the cost is stable. Do these three function until the cost is stable. When the cost is stable, we will get the optimal solution. Until then, we have to do the same three function which I told above from the previous three slides. And coming to the one more functions, reduce gasp and expand gasp. In this, we have two more arguments, one with the function, and then one is don't get set work, and the one is with G and R arguments. And finally, we will do this loop until the time is up, and until we don't have any minimization. Until the minimization is available, we can't reduce further, we can't modify further function. Until then, we have to execute the program. Okay.
Hello everyone, this is Kaustubh. Moving further in our topic, let's discuss about espresso algorithm flowchart. So the espresso algorithm aims to find the minimal sum of product SOP representation of a given Boolean function. So minimal means the expression with the fewest product terms, that is implicants, and the fewest literals, that are variables or their complements in each term. This directly translates to a simpler and a cheaper digital circuit implementation. So there are key stages of this algorithm. So at first, the first stage is start or input Boolean function. So the process begins with defining the Boolean function that you want to minimize. This can be represented in several ways, that are truth table, PLA. PLA stands for programmable logic array file, and Boolean equations. The very next step is generate initial cover, that is cube representation. The algorithm transforms the initial function representation, a truth table and equations into a cover. The third step is expand. So the expand step takes each cube in the cover and tries to make it larger, that is cover more min terms. This is done by selectively dropping literals, that are variables or their complements, from the cube. The goal is to create prime implicants. So let us first understand what is a prime implicant. A prime implicant is a cube that cannot be further expanded without covering min terms that are not in the onset of the function, that is covering minterms where the function should output 0. And then going to the fourth step, that is irredundant cover, that is an optional step. So this step aims to remove any redundant cube from the initial cover. A cube is redundant if removing it doesn't change the function of being represented. And the fifth step is essential prime implication identification. As you can see in the block, after expansion we identify essential prime implicants. An essential prime implicant is one that covers at least one minterms that no other prime implicant covers. So if it is a yes, then we go further for the reduction process, that is reduce block. So this is a key step where the prime implicants are reshaped and reduced to potentially allow further expansion in subsequent iterations. Then we move forward for reshape, check for termination, and if it is a no, then we go to output minimal cover, that is minimized SOP expression. Once the algorithm terminates, the final cover represents the minimized sum of product expression for the Boolean function, and this is the desired result. PLA file format examples. So let us take a file for a 4 input and 1 output function. So at first we can see .i4, which means there are 4 inputs to the system. .o1, which means there is one output from the system, and we can see many things like 1100 space 1, 1000 space 1. So these are all the values of ABCD for output 1. So here each row represents an input combination and so moving further, we have handling don't care conditions. So don't care condition provide flexibility in minimization. It represents input or output combination where function's value doesn't matter. So in PLA format, don't care is indicated by a minus symbol, or we can say dash symbol. For example, we can take 0110 dash and don't care output for the input 0110. Let us take a simple example for Boolean minimization. So let us consider a 4 input 1 output Boolean function. So the truth table encoded in PLA format. The function has a several minterms, which means input combination producing one. So it can be visualized using K-map. So Espresso processes this function to find the minimal SOP expression, which results in minimized expression, that is Q equals to A dot B dot D plus A dot D bar plus B bar dot C dot D bar. So this expression contains three product terms that is implicants. So each term corresponds to a prime cube in n-dimensional space. You can see a table which is a K-map representation here of our equation. The equation was Q equals to A dot B dot D plus A dot D dash plus B dash dot C dot D dash. So this represents the minimized form with three product terms. Moving further, we'll see minimization with don't care states. So with don't care states, that is represented by X, Espresso can choose to treat X as either 0 or 1. So if it is treating as 1, allows for creating a larger implicants. So Espresso will make that choice. So this flexibility often leads to simple.
So moving on to the next topic, application in VLSI designs. In VLSI designs, minimizing logic expression plays a crucial role in optimizing hardware efficiency. By reducing complexity, we can achieve fewer logic gates, silicon format footprint, lower power consumption, and improved overall performance. So one powerful tool that aids the process is ESPRESSO. It has been seamlessly integrated to commercial EDA tools. This optimization is particularly valuable in synthesis stage of SC design, that is the application specific integrated circuit, where even minor improvement can have a significant impact. ESPRESSO is essential for refining control logic in processors, ensuring the efficient implementation of complex state machines. In modern mobile devices, where area and power constraints are stringent, these optimizations are critical for achieving both performance and energy efficiently. So by leveraging advanced logic minimization technique, we can push the boundaries of high performance, low power VLSI designs. Programmable logic devices. Optimal logic minimization is essential for maximizing efficiency, especially in resource limited architectures such as PLA, FPGAs or CPLDs. So the Espresso algorithm plays a key role in this process by generating compact implementation that makes the most available resources. By minimizing logic, it enables complex function to fit into smaller, more cost-effective devices while also reducing routing congestion in FPGAs. Additionally, Espresso enhances timing performance by reducing the number of logic levels, ensuring faster and efficient circuit operation. This optimization is crucial for embedded system where space, power, and cost constraints demand maximum functionality with minimum resources. Through logic minimization, a designer can push the limit of programmable hardware, achieving greater performance, efficiency, and scalability in modern digital systems. So moving on, while Espresso is a powerful tool for logic minimization, it is important to recognize its limitation and concentrations as well. As a heuristic algorithm, it does not always guarantee a globally optimal solution. Instead, it provides near optimal results, which are generally sufficient for large-scale problem where finding a probably optimal solution is computationally infeasible. For critical applications, several important factors must be considered. One key question is whether a manufacturer disclaimer for life-critical applications have a valid legal and ethical defense. Additionally, should advanced ICs be excluded from life-critical systems due to their complexity and unpredictability? So the trade-off between theoretical optimality and practical feasibility is fundamental challenge. Ensuring appropriate verification and validation is crucial, particularly in safety critical systems where reliability and predictability are paramount. Ultimately, designer must strike a balance between optimization, reliability, and safety to achieve the best possible outcome in high-stake applications. In conclusion, Espresso is anytime algorithm, meaning it continuously refines solution until no further improvement is possible. This approach allows it to generate near optimal logic minimization efficiently. So one of its key strengths is its ability to handle very large circuit, processing up to 10,000 literals, 100 inputs and 100 outputs, a scale that makes it invaluable for complex digital design. Even with such a large circuit, Espresso remains highly efficient, completing optimization in less than 15 minutes on a high-speed workstation. Its balance of speed, scalability, and effectiveness makes it a vital tool in modern logic synthesis and VLSI design. So this presentation was brought to you by Sandeep Sharma, Kaustav Kisle, myself Harsh and Kasim Deola, Yogi Murli Krishna. Together, we explored the power of espresso in logic minimization, VLSI design, and programmable logic devices, highlighting its efficiency, application, and key consideration. Thanks for watching.